The whole exercise related to the space physics question, as we did the first 20, so we'll do question 21 today, 21 and 22. This question is about the stars. Describe the stage, sorry, describe the stages in the evolution of a star similar to that, the mass of a sun. So whenever they refer this statement similar to mass of a sun, what does it mean? Low mass star or high mass star?
Low mass star.
Low mass star, because the low mass stars have, we consider them as, they have the same as or similar to that mass of a sun. And for a low mass star, the stellar evolution, like how they evolve. So first, what we have from star, it will form a protostar is their formation. Then a protostar will turn into a main sequence star, and then main sequence star to red giant, then red giant to white dwarf, and white dwarf to black dwarf. But you have to describe them, like, as I mentioned the points. We have first a protostar is there from interstellar cloud. And then the protostar, here I wrote proton, it's protostar. The protostar turn into a main sequence, then a main sequence will turn into the red giant, and the red giant will turn into the red giant will turn into white dwarf. And then white dwarf to black dwarf. You have to, this is what I just mentioned, a sequence. But what you have to do, not only the sequence you have to mention how it happened or how it occurred for each stage. So initially, what we have, the interstellar cloud, which mainly consists of hydrogen, helium, and the dust. And when they all like come together, as a result, what will happen? The gravity increases and the hydrogen fusion start. And once the hydrogen, it is a protostar. Once the hydrogen fusion start and the radiation pressure balances with the gravitational pull, it will be a main sequence star. Once the hydrogen fusion ceases, like hydrogen fusion decrease in rate, again the star will collapse, and this collapse will reduce the size a bit, and that increases the temperature again, and that temperature is sufficient to start a helium fusion. And when it starts a helium fusion, it will turn into a red giant. Once the helium fusion ceases, now again the star will come in like try to collapse or collapse. As a result, it will be a planetary nebula, which result in a formation of a white dwarf, leave behind most of the matter in the surrounding, and the central core will turn into a white dwarf, and that white dwarf will turn into a black dwarf. Next, in part B, the process of energy releases in the core of a star is different to a process of energy release in nuclear power station. Describe how these processes of energy release are different. In nuclear power station, which nuclear reaction occur? Nuclear power
fission.
Fission, good. So on a nuclear power station, there is a fission. And what happened in fission? A fission, the heavy nucleus break down into a lighter nuclei by the help of a neutron. But the core of the star, what happened? The nuclear fusion happened. The lighter atom joined to form the heavy. So you have to basically write a difference between fission and fusion rather than about stars or power station, how they're different from each other, how a fission is different from fusion. So First, we'll mention in a power station, nuclear fission happen or occur, in which the heavy nucleus break down into a lighter nuclei by the help of neutron. And opposite for fusion, lighter on the stars, the core of a star, the nuclear fusion happen or occur in which the lighter nuclei join to form the heavy. And fusion release more energy than fission. Like one fusion produce more energy than 1 mole of a fission. So the star use fusion, and power station fission, and then mention the differences between them. The next part, you can use a screen annotation to complete that. Actually, it's like the blanks are there. The passage describes the evolution of a star with the mass that is much larger than the mass of a sun. So if they're saying that the mass is much larger than the mass of a sun, so they're asking the life cycle for a massive star. And for a massive star, if you remember, like what we have discussed, it's a protostar with the first hydrogen, and rate of fusion is much higher. Of hydrogen fusion is much higher, and they remain in a main sequence for a very short span. So the next one, as you can see, the words are there. I have to zoom out so that it's readable. So one by one, we will discuss each. The first one, the hydrogen atoms in a nebula move. Even if you want to learn as an answer the life cycle of the massive stars, you can learn from this paragraph. Like that's also actually an answer. The hydrogen atoms in a nebula move towards each other due to a force of gravity. As the atom move towards each other, their dash increases. What increases? Which one I should use from the? You can, instead of writing, you can just circle that, so it will save time. When the particles come closer. So first one, that's right. So their kinetic energy increases. Because as they come closer, the gravitational potential energy decrease. So the kinetic energy increase. The next one, the store increases, like their dash energy store increases, which increase the temperature. If the temperature become high enough, the nuclear fusion of a hydrogen will start, and star enter the dash stage of its evolution. Which stage of evolution it? The second blank. Which stage of evolution they enter? Is it a protostar or a main sequence? Actually, protostar is like start of it. Main sequence is when the hydrogen fusion started and it balanced the radiation pressure. So the correct answer with reference to the question is the main sequence. Why not protostar? Why they don't accept protostar here? Because protostar is when all the things are coming closer to each other, that phase is a protostar. And it's just a hydrogen fusion started. But when hydrogen fusion started and it balances with the radiation pressure, like gravitational pull balance with the radiation pressure, it become a main sequence star. So even this part, when the hydrogen atom in a nebula move towards each other, that is a stage where it become a protostar. So this should be a main sequence star. The next one, the hydrogen fusion stop in the core, and the core of a star will start to dash. What will happen to the core as the hydrogen fusion stop? The core will start to what? Expand or a contract? What will happen to the core? The hydrogen fusion stops. If the hydrogen fusion ceases, the radiation pressure decreases. So due to smaller radiation pressure, the core will become contract. The size will decrease. And when the size decrease, this increases the temperature in a layer surrounding the core, and hydrogen fusion restart in a layer surrounding the core. This causes the star to dash. So what should be the answer here? This increases the temperature in a layer of surrounding core. As a star collapse, a hydrogen fusion restart in a layer surrounding core. This causes the star to dash and its surface temperature decreases. Again, the fusion started. So what will happen to the star? So if the fusion again started, then the star will again will expand. And this star is now a red giant. So here we will have expand. Then the star is now a red giant. Eventually a nuclear fusion stop. The core of a star and the star explode as. So when the core will explode, what it will become? So like what will explode as a supernova? That explosion is basically known as a supernova. And from this supernova, the core of a star collapses to form either dash or a black hole. What it can form? White dwarfs are formed for low mass stars. White dwarfs are for low mass star. So if I write, yeah, the neutron star is the correct answer. So what if I write the two cycles for a low mass, which is like sun-like stars, and the high mass star, which is 8 times the solar mass. Here we have a protostar. Protostar. The protostar will enter a main sequence once the radiation pressure is equals to the gravitational pull. This will also enter a main sequence, but it will have a smaller lifespan in a main sequence. Then from main sequence, once the hydrogen fusion ceases, it contract and collapse, and it started a helium fusion, and as a result, it will become a red giant. This started when like a helium fusion. As a result, the size will be much bigger. So we can say a red supergiant, or you can also say blue giant. So blue giant or red supergiant, same idea, same thing. Then what will happen? Then it will turn into a planetary nebula, which will result in a formation of a white dwarf. So planetary nebula result in a formation of a white dwarf, and the white dwarf will turn into a black dwarf. But this due to planetary nebula. Here what will happen due to supernova? It will either form a black hole or a neutron star. So these are the possibility for a low mass and the high mass stars. In question 23, we have a red supergiant which has a mass much greater than a sun. Describe the evolution. So it's the same idea, like it's the same answer here. if you write, it's the same question. Describe the passage evolution of a star that is much greater than mass of sun. So if you write all the points here, you will score the mark. Like you'll mention what we'll mention hydrogen atoms in a nebula move towards each other, gravitational force, due to gravitational force, as atoms move towards each other, their kinetic energy increases, which increases the temperature, and the star become hot. The nuclear fusion of hydrogen start, and it enter a main sequence. Then when hydrogen fusion stop the core at the core will start to contract, and this increases the temperature. Even this increases the temperature of outer layer, or you can mention this increase in temperature cause a helium fusion also. So here you can also mention a helium fusion start, not restart, this will be start. And this causes the star to expand and its surface temperature decrease. The star is now a red supergiant or a blue giant, and eventually a nuclear fusion stop in the core, and the star explode as a supernova. The core of a star collapse from either to form a neutron star or a black hole. So question 23 is the same answer as 22, but in 22 it was blanks, in 23 it is structure. Question 24. This question is about the astrophysics. Complete the sentences by writing a suitable word or a phrase in each blank. You can use screen annotation to complete this. Space in all galaxies in it is called the universe. A large collection of billions of stars is called a galaxy. And sun its collection of a planet moons is called a solar system. Yeah, that's right. The second one, the diagram shows the orbit of a comet around the sun. You can use screen annotation. At which point in its orbit the comet moves fastest? A, B, C, or D? At point A, because at point A it is closer to the sun, so potential energy is least and the kinetic energy is maximum. Yeah, right. Name the force that keep the comet orbit the sun. Which force is causing it to orbit the sun? Gravitational instead of GPE, you cannot say GP. GPE means gravitational potential energy. It's a gravitational force. Next, the boxes give some units of time and some definitions. Draw straight lines. Match. This you have to match. Unit of time, 1 day is equivalent to what? You can use the screen annotation to match. 1 year is a time for the Earth to orbit the sun. That's true. What about 1 day? 1 day is a time for Earth to rotate once. The time for the moon to orbit the Earth is that refers to the time period of the moon, or which is about 27 to 28 days. The diagram shows two objects orbiting a star, X and Y. Object X has a circular orbit. State the type of object that has a circular orbit around the star. How it cannot be a comet. It should be a planet. The next one, object Y has elliptical orbit around the star. State the type of object. Yeah, so elliptical is comet. Object X completes the orbit of a star in 335 days. Calculate the orbital speed. The radius is given. Look, usually like this time period is given, the radius is given, we need the orbital speed. So object X is moving in a circular path. Your orbital speed is orbital distance over time. And what is the orbital distance as the object is moving in a circular path? So if this radius is r, so we'll say speed is distance over time. So distance will be equal to 2 pi r and the time is t. So speed is 2 pi r divided by t. So in this case, when we take so this will be equal to speed is distance over time or 2 pi r. So this will be 2 pi is 3.14 where r is the radius which is 1.5 into 10 to the power 11 meter. And time is in days, like 35 days. We have to convert first we have to convert days into hours and then hours into minutes and then minutes into seconds. So 35 days multiplied by 24 will convert into hour, multiply by 60 minutes and multiply by 60, this will be in second. What's the final answer? When you divide
311,507.
311,507 and the unit will be meter per second. So this is a orbital speed of this or object X, which is actually a planet. Hertzsprung-Russell diagram shows a relation between the absolute magnitude and the color of the star. The position of a sun is shown here. You can see like this is the position of a sun. Then a white dwarf is a star W is a white dwarf. Add a letter W to an Hertzsprung-Russell like W is a white dwarf and white dwarf have which position we can find these white dwarfs. Look, what is the concept of absolute magnitude? Like absolute magnitude means when we compare the objects, like say this is a place we are observing an object and we have two. This is the absolute magnitude, like we are observing two objects from Earth, object 1 and object 2. So we consider this, the one which is giving out, like one is giving more light, one is giving smaller light. So the one which is giving a smaller light, we consider that, or a specific distance, both are as the same distance. So we say this absolute magnitude is 0. Compared to this, how much magnitude or intensity of a light is coming. So plus 5 means like 5 times more is there. Minus 5 means 5 times less is there. So when we compare, like we have sun and other star, so their sun absolute magnitude is given 5. So which region will have a white dwarfs? These white dwarfs have a high temperature. The temperature of a white dwarf is higher. So where we can find the white dwarfs, we can find here in this region. That's right. Like, and from the name, you can identify their white dwarfs, their temperature is higher. So this is for low temperature. This is for high temperature. Then star X is a red giant. Where we can find red giant? From the colors, you can also identify like where you will have a red giant. Which region will have a red giant? In an absolute magnitude, the red giants should be here. So what is the concept of absolute magnitude? Yeah, how you will identify, look, for example, you have red giants, you have a red giant, you have a sun-like star, and you have a white dwarf. White dwarf, I cannot draw white here as a background itself is white, so you will not see. But example, I have white dwarf. Now what I have to do, like all are in one line. I will give a simple concept of absolute, like there's a race between a red giant, a white dwarf, and a sun-like star. And we are observing from the earth. So if I want them to, if I want the same, if I want to have a same intensity of a light from all of them, I call this as a zero line, origin. If I want same amount of the light from all of them, so what I should do, because the white dwarf is having a smaller size or lower luminosity, so I should move the white dwarf, like this is a white dwarf, this one is sun-like star, and this one is a red giant. So I want to receive the same amount of intensity for all of them. But if they're all on the origin, I will receive more intensity from red giant. I will receive smaller amount of intensity from white dwarf. So I should move the white dwarf closer. The white dwarf should be like 10 times closer to us. Sun also move closer to give a certain intensity, like if from origin. And the red giant should be moved away from the origin so that I will receive the same intensity of the light from all of them. So if I say sun is at +5, where like sun cover +5 from origin, sun is +5 ahead. So red giant, white dwarf, to give the same light intensity as the sun, it should be like example around 10 or +10 times closer. And what about the red giant to give the same light intensity? So it should be away from the origin. That's why it is -5. So we want to receive the same amount of light from them. So if we start all of them from the same origin, which position red giant should move, which position sun should move, and white dwarf, so that we have a balanced radiation or same amount of radiation from all of them. That is the concept of the absolute magnitude. So they give you a reference. It can be any number. It's not like +10. It can be any number, but for a white dwarf, it can be any number, but it should be more than the sun. Like to receive the same intensity, if the sun is moved like 5 units, if I move sun 5 units, I should move white dwarf more than 5 units. So any value should be more than 5 for white dwarf. And to get the same light intensity, the red giant should be moved away from the origin. So that will be in negative intensity, like negative absolute value. So when we complete this, what are the positions where we should have a white dwarf? So white dwarf will be somewhat here in this region, and where we should have red giants to have the same intensity. Is it clear? Like plus means it should move towards us, negative means it should move away from us. Anyone having a doubt in this? Then star Y is a main sequence star that is much larger than the sun. Add a Y Hertzsprung diagram to show position of a Y. So where we should have a Y, like we have a white dwarf here that we label as W. Then X is a red giant and Y is a main sequence star. So W is a white dwarf, X is now a massive star there's another star which is massive. To get the same light intensity, where I should move. Like example, if I say I have a sun-like star, not sun-like star, a mean sequence star, but which is larger. So to get the same light intensity, how much I should move from origin? More than sun or less than sun? If I have another star, but which is a massive star compared to, so I should move less than sun. It should be positive, but less than sun. So when we label the white dwarf was here, the red giant X was here. So where will be Y? So Y will be here. And star Z has the same surface temperature as the sun, but would be dimmer than the sun. If it were the same distance from the Earth as the sun, add Z to a Hertzsprung diagram, show position of a Z. So like star Z is same surface temperature as sun, but would be dimmer than the sun if it were the same distance. So where we have to show the Z, so in that case, the Z will be below the sun. So we have the white dwarf here. We have a red giant here. We have a star which is more than the sun, and we have a star which is smaller than the sun. Is it clear?
Yes, sir, clear.
The moon is brightest object in the night sky. Suggests why the moon cannot be shown on the Hertzsprung-Russell diagram. Hertzsprung-Russell diagram is actually for objects which are luminous objects, like they're giving out their own light. So it reflects the light of a sun. That's why it cannot, because all these are stars here, which are luminous objects. They are giving their own light. But sun, the moon is not giving its own light. So moon appear to be bright in the night sky, but why we cannot show in the Hertzsprung diagram? Because this diagram is only for luminous objects, those objects which give their own light. Sun is giving its own light, white dwarfs giving their own light, red giants giving their own light, massive star giving their own light, and even low mass star less than sun are also giving their own light. We can represent them, but we cannot represent moon here because moon is not giving its own light. It's for luminous objects. Then the Big Bang theory suggests the universe is approximately 14 billion years old. Describe an evolution of a universe from Big Bang until the present day and describe the evidence which support a Big Bang. There's a last question. So like how the universe have evolved from the Big Bang. So universe in the beginning, it was very hot and dense and has expanded since the Big Bang, and it is in a cool down state. So universe was very dense and hot. And the Big Bang, what actually happened to the universe? The universe expanded since the Big Bang. And the universe is actually in the cool down stage. Since the Big Bang. The next part, we have to give an evidence. What are the two evidence which support the Big Bang theory? One is the cosmic background radiations. Yeah, redshift and the cosmic background radiation. So presence of the cosmic microwaves. So the presence of the cosmic radiations that is same from alter direction, like shows that there's a uniformity in the spreading of the universe. And redshift of the galaxies shows like galaxies are moving away from each other. So these are the 2 points you should always include whenever you give an evidence of a not planets, galaxies, because planets are not giving out their own light. So we have to use the term galaxies or the stars. So 2 points. Number one, the presence of the cosmic background radiation, which is same throughout. One mark for presence of a cosmic background radiation, 1 mark for radiation come from all direction. That is one evidence. Second is the cosmic background radiation, redshift is there from different galaxies. And when redshift is there, it means the universe is expanding. Also an evidence of a Big Bang theory. According to Big Bang, as start from one dense point, and due to the Big Bang, everything scattered. So this also an evidence, the redshift also an evidence of a Big Bang. So these are the 2 pieces of information you will always use whenever you refer to a Big Bang theory. Is it clear? This was the last question from space physics exercise.